All right, so in this lesson, I'm going to go into detail about single replacement reactions, and you're actually going to learn how to predict the products for a single replacement reaction, and then we'll actually see it in the lab. Okay? So remember, in a single replacement reaction, one element goes in and kicks out another element from a compound. Now, how exactly does that work? Well, in a single replacement reaction, a positive ion, which is called a cation, and yes, this is going to be corny, but this will help you remember it. A cation is positively charged, like the paw in a cat, all right? So a cation, a positive ion, will switch with another cation, with another positive ion. Okay, and I'll explain what that means in just one second, okay? A negative ion, which we call an anion, will switch with another negatively charged ion. Okay? And when we're writing these compounds, guys, remember these are ionic compounds that we're dealing with, and so the metal or the cation always goes first. So we always write the cation or the metal followed by the anion or the nonmetal. So in order for this to make sense, let's look at some examples, okay? Before I do that though, I need to explain what this activity series is on the right-hand side. Basically, in order for any of these elements to kick out another element, they have to be higher on the activity series. If they're not, then you will not have a reaction and you will just write no reaction. So let me go through and show you some examples of both positively charged ions kicking out positively charged ions, negatively charged ions kicking out negatively charged ions, and the use of this activity series. So let's look at zinc and silver nitrate. All right, zinc right now is not a cation, but when it does form an ion, because it is a metal, it will form a positive charge. Remember, zinc has a 2+ charge. So a positively charged ion, or an atom that forms a positively charged ion when it is an ion, is going to kick out another positively charged ion. Well, silver in this case is my positive ion because it's first. Remember, your positively charged ion goes before your negatively charged ion. And I also know its charge, it's +1. So zinc is going to go in and it is going to kick out silver. In order for zinc to kick out silver, though, it has to be higher on the activity series. So let's check this. Well, zinc is right here, and silver is down here, so I am good. Zinc is higher on the activity series than silver, so it will in fact kick out silver. So let's go back. Zinc is now going to form a new compound with nitrate, so I actually have to cross charges to figure out what that compound will be. Okay, so zinc has a 2+ charge, nitrate has a 1- charge, so this will be Zn NO3 2. So zinc formed a new compound with nitrate, and then silver got kicked out. So it's going to be all by itself. Remember, silver can exist all by itself because it is not a diatomic element. It is stable by itself. Okay? The last thing I need to do for this reaction is I need to balance. So I've got 1 zinc, 1 zinc, 1 silver, 1 silver. I've got 1 nitrate here, but 2 on my product side. So that tells me I'm going to have to put a 2 in front of silver nitrate, which then gives me 2 silver, so I'm going to put a 2 in front of silver there. Okay, not too bad. Let's do the next one. Now I've got bromide reacting with sodium iodide. So Br2, when it forms an ion, it forms an anion, a negatively charged ion, right? Br-. So Br is not going to kick out Na, it's going to kick out another negatively charged ion, so it will kick out iodine. Okay, let's check to make sure it really will. So this is actually at the top of the activity series. Notice bromine is higher on the activity series than iodine, so the reaction will occur. Okay, so let's actually allow bromine to kick it out. So bromine is going to form a new compound with sodium. So Na has a +1 charge, bromine has a 1- charge, and so this gives me NaBr. Okay. And then iodine got kicked out, so it is going to now be by itself. Do keep in mind, iodine is diatomic, so you cannot just write I, you're going to have to write I2. Okay? And the last thing that I need to do is I need to balance. So I've got 2 bromines on my reactant side, 1 bromine on my product side, so this needs to be a 2 in front of NaBr. Now I've got 2 sodiums on my product side. I'm going to put a 2 in front of NaI. And then that gives me 2 iodines on my reactant side and 2 iodines on my product side. So I am balanced. Let's look at number 3. Number 3, cadmium looks a little bit weird. And the reason why I put cadmium 2 is simply because otherwise, if you look at the periodic table, we won't know the charge of cadmium. So that's why I include this. It has nothing to do with our balancing at all. It's just a, hey, by the way, when it does form an ion, it's not an ion right now, but when it does, it will have a 2+ charge. All right, so cadmium, 2+ charge, so it will kick out another positively charged ion, another cation, so it'll kick out hydrogen. Let's double check to make sure that'll actually happen. Well, cadmium is here, hydrogen is below it, so that reaction will occur, okay? So cadmium is gonna kick out hydrogen, so it will form a compound with oxygen. Cadmium has a 2+ charge, oxygen has a 2- charge. When I cross my charges, keep in mind you get CD2O2, but you've got to simplify that, so it's gonna just be CDO, okay? And then keep in mind, hydrogen got kicked out. Well, hydrogen cannot exist by itself. It can't just exist as H. It's going to exist as H2. All right? Now I've got a balance. I have 1 cadmium, 2 hydrogens, 1 oxygen. I am actually already balanced. Okay? Let's look at example number 4. F2 reacts with AlCl3. Well, fluorine, when it is an ion, is negatively charged, so it will kick out the negatively charged chloride ion. Let's make sure that actually happens. So let's go back to the top of my activity series. Fluorine is here, chlorine is here. Okay, so fluorine is higher on the activity series, so that reaction will occur. Okay, so fluorine will form a new compound with aluminum, so I've got to figure out what that'll be. Notice I put aluminum first because it is positively charged, and fluorine behind it because it is negatively charged. So this will form Al, when I cross charges, F3. Remember, chlorine got kicked out, so it will exist by itself. But remember, since chlorine is diatomic, it can't actually exist by itself, so it's going to be Cl2. All right, now I need to balance. I've got 2 fluorines and 3 fluorines on my product side, so I want to make that equal to 6. So I'm going to put a 2 in front of aluminum fluoride and a 3 in front of fluorine. Now I've got 6 on both sides. For aluminum chloride now I need a 2 here so that I'll have 2 aluminums on both sides. Now I have 6 chlorines, so I've got to put a 3 in front of chlorine there to make 6, and I am balanced. Okay. For the last one, silver reacts with hydrochloric acid. So silver has a positive charge as an ion, so it will kick out another positively charged ion. Okay. If you notice, silver is here on the activity series while hydrogen is here. So silver is actually lower on the activity series than hydrogen. So if I put silver in hydrochloric acid, you would not see anything. There would be no reaction. Okay, let's talk really quickly about what you might observe when you have a single replacement reaction. So let's look at my products here. Okay, so zinc is a solid. Silver nitrate is going to be aqueous because I'm going to have it dissolved in water. I'm letting you know that. I didn't expect you to know that already. Okay, so zinc nitrate is going to be aqueous because what's going to happen is the zinc is simply going to form a new compound with the nitrate and it's going to stay in solution, while silver, because it's a metal, will be solid. So what you will actually see, if I said, hey, how do I know that that reaction actually occurred? You could say, well, I know it because I would see silver forming, solid silver forming in the solution. Okay, for the next one, I've got bromine reacting with sodium iodide. How would I know that this reaction is happening? Well, sodium iodide is probably going to be aqueous because these compounds tend to be. I have them dissolved in water just to help them react to make it easier. So this will probably be aqueous. But iodine is now going to be all by itself. Well, if you look up iodine is actually going to be a solid, and you'd have to look this up. I don't expect you to know this, but it tends to be a solid when it's by itself. So you would see solid iodide forming. Okay? What about for number 3? Well, you would see cadmium oxide would probably be a solution. But the most obvious thing, H2 is a gas. So you would see bubbles forming. So you could confirm that hydrogen gas forms. Okay? So while when we're in the lab, we might not see that zinc nitrate is forming, by being able to observe that a solid is forming and seeing that it is silver, we can confirm the reaction that we predicted. Just like for number 2, if we see solid iodine forming, we could confirm that this reaction occurred. Or if we saw hydrogen bubbles forming, we could confirm that that reaction occurred. So when we work with single replacement reactions in the lab, our way of confirming that the reaction we predicted was correct is simply by our observations, what was forming. And a really nice way to confirm our predictions is if nothing occurs, right? Because if a reaction occurred for number 5, if something changed, then we know that we did something wrong in our predictions.